Let's do a short review of polar covalent, nonpolar covalent, and ionic bonding. This goes back to the very first webassign that you did. Do you remember when? Do you remember when? We were taking electronegativity differences. And if the difference was less than 0.3, it was a nonpolar covalent bond. Do you remember when? Do you remember when? We took electronegativities were 0.3 to 1.6. Were polar covalent bonds. Do you remember when? Do you remember when the difference in electronegativity was greater than 2.1? That it was an ionic bond. Do you remember when? Do you remember when? Do you remember when? That left us with a problem between 1.6 and 2.1. Do you remember when? Do you remember that if it fell in between those, if there was a metal involved, it is an ionic bond? That if it fell between 1.6 and 2.1 and nonmetals were involved, that it was a covalent bond? Do you remember? Good. I'm glad that you remember. Because we're going to start talking about whether something is shared equally, whether it's unequally shared, and we've already talked about the transfer. So, we can relate an equal sharing of electrons with a nonpolar covalent bond. We can relate an unequal sharing of electrons with a polar covalent bond. So, once again, I just included this little chart up here, and I probably should put that to 0.3. I didn't change that one because if you remember, I switched the numbers from 0.3, from 0.5 to 0.3. So, probably should have changed that. Sorry I did not. Nonetheless, that's how we are relating a polar covalent bond, a nonpolar covalent bond, and an ionic bond. With the equal sharing, the unequal sharing, then the transfer of electrons. Now let's look at these two electrons. I have a hydrogen, okay? I have a hydrogen, which, that brings up the point, folks. That brings up the point. I didn't talk yet about exceptions to the octet rule, but hydrogen is one. Why is hydrogen an exception to the octet rule? It only has 2 valence electrons to fill its outermost energy level. Excellent. Okay? So, hydrogen is an exception to the octet rule. Now, as I look at electronegativities between hydrogen and fluorine, okay, I look at electronegativities between hydrogen and fluorine, and I see 3.98, 2.20 for a difference of 1.78. That falls into my gray area, doesn't it? Okay? Now when I look at that gray area, am I dealing with a metal? Hydrogen is not a metal, it is a gas. Hydrogen is a nonmetal. So, when I go back, here it says, if nonmetals are involved, the bond is considered polar covalent. So, what type of a bond is made between hydrogen and fluorine right here? A polar covalent bond. We know that. Okay? So, When I look at this, I have shared electrons right here. I have unshared electrons, unshared pair. Okay. Unshared pair, shared pair. Now, let me ask you this. We got our tug of war, don't we? We got our tug of war. Is anybody winning the tug of war here? Who's winning the tug of war? Fluorine. That's going to be important coming up later. Okay? Fluorine is winning that tug of war because fluorine's electronegativity was 3.98. Hydrogen's was only 2.20. So fluorine's winning that battle for those electrons. Okay? So, once again, this is a polar covalent bond. Now let's look at this one. Let's look at this one. Bromine, lithium. 2.96 minus 0.98 gives me a 1.98. That definitely falls into my 1.6 to 2.1, doesn't it? What can you tell me about lithium, though? Lithium is a metal. So what type of bonding do I have here? Ionic. This is an ionic bond. So that bromine will transfer or pull that electron, that one lithium electron, over here to fill its octet. So that is a transfer. That electron is transferred from lithium to bromine. I'll give you a second here to write this down. The summary of the number of bonds made by each non-metal element, the number of electrons are needed to complete the octet. Remember when we talked about nitrogen? How many electrons were needed to complete the octet? 3. So what do you think it's going to do? Triple bond, right? Now let's look at something we did not talk about. Look at sulfur. Look at sulfur. If you were going to guess what type of bonding sulfur likes to do, what would your guess be? Single, double, triple? Double. Why would you think double? Because it has 2 openings and it needs 2 electrons, right? Let's look at iodine, way down of the halogens. Okay? Way down of the halogens, iodine. What do you think it would like to do? Single, double, or triple bond? Single bond because it has 1 electron that is needed. So that's a generalization that can be done, okay? That usually, if we count the number of electrons, okay, if you count the number of electrons, then we have the number needed. Now this next slide here, this is very important, okay? This is very important, and I would like you to draw this exactly how this is in your notes. This is a diagram, folks, that helps us determine what type of bonding will be occurring, okay? This shows us that up at the top, these elements right here, other than hydrogen, those elements are all halogens. But what is the similarity between all of those elements right there? What's the similarity they have? They only need 1 electron to fill their outermost energy level. So those are going to single bond. Okay? Now, could it be an ionic bond? Could it be a covalent bond? Could be either. But it's only going to be dealing with a single bond. Now, let's look at the second one. Okay? The second row. These right here. What do they have in common? What do they have in common? 2 electrons to fill their outer shell. So, they could have a double bond, or they could have 2 single bonds. Okay? But either way, the total number equals 2, right? A double bond or 2 single bonds. Now, these next 2 are similar. These next 2 are similar because they both have what? 3. They need 3 electrons to fill their outer shell. So how could they do it? Well, they could do it 3 different ways. We could have a triple bond. We could have a double bond with a single bond. Or we could have 3 single bonds. But either way, they're all adding up to be 3, correct? Now, carbon is the last one. And we have a whole big group of things that we call hydrocarbons, which is the building of carbon chains. Okay, carbon to carbon bonds. If you look at carbon, how many open bonding areas does it have? 4. So it's going to want to have a combination that equals 4. Now, we talked about the quadruple bond, right? What did we say about a quadruple? Ain't gonna happen. Okay? We don't have a quadruple bond. So you can see that carbon could have 4 different types of bonding that it could do. Carbon could triple bond with a single bond. It could have 2 double bonds. It could have a double bond with 2 singles, or it could just have 4 single bonds. Okay? This diagram is going to be very important in the next coming days, weeks. It's going to be big when we talk about Lewis structures, and I believe that is tomorrow. Last thing we're going to do today is we're going to talk about dipoles. We're going to talk about dipoles. What is di? 2. So dipole literally means that there are 2 poles. There are 2 poles. A dipole is a molecule in which one end of the molecule has a partial positive charge and the other end has a partial negative charge. Overall, the molecule is neutral. Number 1, we're talking about molecules. So what does that tell you? Tells you what? Two atoms, well, there could be more than two when we're talking about these poles, but covalent bonding is the big thing, okay? Covalent bonding, I agree with you, it's between two different ones, okay? Two different atoms, but a molecule tells us that they are covalently bonded. So what's going to happen in this dipole is somebody is winning the tug of war. Obviously, on this one, who's winning the tug of war? Fluorine. How do we know fluorine wins the tug of war? It has the highest electronegativity of anything. So, when I look at those electronegativities, fluorine's a 3.98, bromine's a 2.96. Both are still pretty high, right? In terms of electronegativities. Okay, both are still pretty high. When we look at those, okay, I didn't do the math. Okay, I didn't do the math. What's that going to be? 1.02? If I do it right, so that's going to tell us that it's a polar covalent bond when I do the math. Now, who's winning the tug of war? Fluorine. So how we signify that is by these little things right here. Okay? That means, that little symbol means partial. So that is a partial negative. Why is it a partial negative charge? Because this fluorine is pulling these two electrons closer to it. Okay? Closer to it. Does it pull it all the way? No, because then it would be a negative charge. Okay? Doesn't pull it all the way. So if that's a partial negative, the bromine's going to end up being a partial positive. Okay? A partial positive. Another way that I've seen this written, is they have a plus sign with an arrow pointing like this. So the arrow would be pointing to the negative end, the one that is pulling more. I'll show you that here in a second, but that's just to make note, that arrow with the plus sign at the end of it. Now let's look. So this is right here a polar covalent bond. And looking at the dipoles, this end's partially negative, this end's partially positive. Now let's look at carbon dioxide. Okay, CO2. I can see that I have two double bonds here. Didn't we say that carbon could double bond on both sides? Yeah. So I've got carbon double bonded with two oxygen, CO2, carbon dioxide. Now look at the electronegativities. What's the electronegativity of carbon? What's the electronegativity of carbon? 2.55. What's the electronegativity of oxygen? 3.44. So, who is winning the tug of war between these four electrons? Oxygen. Now, we're going to break it down, okay? So, we're looking right here at this bond right here. Okay, so we're looking at that bond right here. Who's winning the pull for those four electrons? Oxygen. What about this one? Who's winning the pull for those four electrons? Oxygen. So when I put in my partials, both ends are going to have partial negatives. Okay? Both ends are going to have partial negatives. The middle is going to be a partial positive. Now, here's the rub with this. Here's the rub. These bonds are polar. Those bonds are polar. This molecule is not, though. Okay? You say, how can that be? Those bonds are polar, but the molecule is not. The best way I've seen to show this is, Ken, go ahead and stand up, okay? John, go ahead and stand up, okay? Come over here. Now, the three of us right here are carbon dioxide. Here's carbon, and we got the two oxygens. Obviously, John and I are pulling at a 3.44, right? So, reach your arms out like this. Here's our double bonds. I've got mine, he's got his. We're both pulling at 3.44. Is anybody winning the tug of war? No. Nobody's winning the tug of war. Now, are these bonds, am I winning against oxygen? Or excuse me, against carbon? Yes, I'm winning. Is John winning against carbon? Yeah, John's winning. But when we put us all together, is anybody winning the tug of war? No. That's why the molecule there is not polar. That's a nonpolar molecule. Okay? The bonds are, the molecule is not. Does that make sense? Now let's check out. See, here's another one where I showed you. Okay? That is what I just showed you, but this is signaling that partial positive, partial negative. Partial positive, partial negative. Look over here at this water molecule. Okay? We know that oxygen was 3.44. What's hydrogen? 2.20. So, as I look at this, the oxygen is winning the pull for this pair of electrons right here. The oxygen is winning the pull for this pair of electrons right here. Do those cancel out like the ones we just talked about here? No, they do not, because they're not pulled in a straight line. Okay? They're not pulled in a straight line. So, this molecule is going to be a polar molecule because this end is going to be a positive. This end is going to be negative. And do those poles cancel each other out? No, they do not. So when we talk about water, we talk about the polarity of the water, where the oxygen end is partially negative. The hydrogen ends are partially positive. Okay? This polarity helps give water some unique properties. Okay? Some unique properties due to the polarity. Okay?